welcome back to the session, right. So, in this session we will discuss about basically the specification of time domain, and then we will discuss in detail about the steady state error present in the system, right. So, in this session we will discuss about the second order system, right, and we will see the time domain specification whenever we apply a step input in the signal and our system is under damped. It means my zeta is less than 1, but greater than 0. Okay. So, we had discussed it last time. So, in today's session we will discuss the expression of rise time, peak overshoot. Okay. Then we will see their application. Then we will discuss about the introduction of steady state error analysis. Then we will discuss error analysis for different standard inputs. Okay. So, this response is the second order response, and whenever my input is a step signal. So, I discuss it, this red line is my basically input, okay, and this line is basically the output coming because of this step input. So, I am getting here delay time, rise time, maximum overshoot, and this is basically the TP, peak time. So, one by one we would like to see the output response, and one more term is getting here, that is settling time TS. So, when we reach to the 95% of the response, in some textbook you will find 98% of the output response, then this will be the settling time of the system. Okay. So, one by one we would like to see their expression. One is here rise time. So, we discussed that our time interval would be from 10% to 90%. You can see here, okay. This expression would be rise time. This is the 10% and this one is 90%. This time interval is rise time. Okay. So, here I am assuming the output response for under damped case. Okay. We discussed it in the last session, where theta is here as cos inverse zeta. Okay. So, here whenever we are discussing for rise time, then my final output will reach to the value of 90%. We can say this y t would be approximately reaches to the value of 1. So, I am assuming this value is 1, it is equal to 1 minus this term at this time instant, my time t would be equal to t of r, which is rise time. So, rise time you are getting here in the expression. Okay. So, if I like to solve it, 1 will cancel out and this will be equate to the 0. Okay. So, here if we see this term is basically you can say this exponential term is not going to 0 here. So, here this sine term it may go 0 for certain values of pi. It means if this angle is pi, then this term would be equal to 0. So, here we can say omega d t r plus theta equal to pi. From this expression we can say rise time is equal to pi minus theta over omega d, okay, where omega d is omega n 1 minus zeta square and theta is cos inverse zeta. So, this is the expression for rise time. So, in the numerical, whenever we know value of zeta and omega n, then we can calculate the rise time. In the same way we will see the expression for peak time. So, for this we have to see what is the peak time, the time interval, you can see the time instant where I am getting the maximum value of the output. So, this time interval basically would be the peak time. Okay. This is the time interval here, or at the instant where I am getting the maximum value, this would be peak time T p. Okay. So, this T p is here. So, I need to calculate this value. So, time T p is that you can say T p is the time taken by step response to reach the peak value. At this peak time you can say derivative of response is 0. So, if I see this response, so if I have to calculate the slope at this value, because my slope is here increasing, after this point my slope is decreasing. Okay. So, this slope is decreasing after this point. Now, a point will come whenever my slope is 0. At this instant I will get the maximum value of the output. This time instant would be here T p. So, here my derivative of dy t over dt would be equal to 0. This will help us in calculation of peak time T p. Okay. So, here that is why I am taking derivative of y t equal to 0 at time t equal to T p. I will use the same output response that I had taken previous. Okay. That is, this will become 1 minus zeta omega n Okay. If you see the previous response, okay. So, I will use this equation y t equal to this equation, and I need to calculate the derivative of it dy t over dt. So, here 1 is constant, it will be 0. First I have to differentiate it, okay. Then sine term would be constant, then I have to differentiate the sine term, this term would be constant. Okay. So, after doing this I am getting this expression. Okay. First I am differentiating it, this term is constant, then I am making this term constant and differentiation of sine, that is cos of this. So, if I further simplify it, I have to equate it to the 0, okay. This term will come, right. So, you can see omega n over under minus zeta square, this will cancel out, zeta will remain here, okay. Or further if I solve it, this will become, if just you can say if I replace zeta by cos theta, we had done this in previous session, and this you can say under root of 1 minus zeta square can be replaced by sin theta. Okay. This will become this expression. If I further solve it by cosine function, this will become omega dtp, okay, and this term would be 0 whenever it is function of pi. So, here my peak time would be, you can say this omega dt Tp is function of pi. So, I can write omega d Tp is equal to pi, then this term would be 0. Here the peak time Tp is equal to pi over omega d. So, this is written here, this is omega d is given by omega n under 1 minus zeta square. So, this is the expression of peak time, and it will help us in calculation of peak time, and it will help us when we solve the numerical for peak time. Now, we need to determine expression for peak overshoot. Okay. So, as per definition, the peak overshoot that I told you in the previous session, it is yTp minus y infinity, you can say output value at steady state divided by y infinity. So, at y infinity, whenever I am applying the step input, the final value is 1. You can see in the graph, my final value is approaching to the value of 1. So, this is my y infinity is equal to 1. So, I have to apply this formula for calculation of peak time. So, you can say this is the maximum peak and this is the steady state, and the difference between them and percent of difference between them will be the peak time. So, this concept we will use here for calculation of peak overshoot. So, here this is the MP equal to this much, that is yTp minus 1. It means I will subtract my output response from 1. So, this is my equation y t equal to this much. If I subtract with 1, this 1 will cancel out, only this term remains. Okay. So, that is why in the calculation, so yTp minus 1 would be given by this expression. Okay. Further, if I would like to simplify it, this is happening at peak time Tp. So, here T will replace by Tp. I have to evaluate value of Tp, that is pi over omega d, we had just derived in the previous slide. I have to put this value. Okay. So, this will become omega d will cancel out, pi plus theta, this minus sign will convert into plus, this is sin theta. In the denominator is here 1 minus zeta square, I can replace it by sin theta. So, sin theta will cancel out from denominator and numerator. So, my peak time peak overshoot would be given by this expression in percentage. So, 100% you can say multiplied by exponential of minus zeta pi under 1 minus zeta square. If I would like to see MP, it is minus zeta pi under 1 minus zeta square. So, this is the expression of peak overshoot, right. In the same way, we would like to see the expression of settling time. It means we would like to see the value of output whenever my output response reaches to the 95%, or in some textbook you will find it reaches to the 98%. Okay. So, here we are using certain tolerance. If it is not arriving at value of 1, you are getting certain oscillation. Okay. If you are saying that my signal is not fixed at, you can say at time t equal to infinity, my output is not settling down, it is having certain oscillation. So, we are having certain tolerance band, this band having ratio of 2% to 5%. it means we can handle this type of oscillation in the system without any problem. So, this band is basically the tolerance band. Okay. So, whenever we are saying our tolerance band is 2%, then settling time is given by this expression. Whenever we are saying our tolerance band is 5%, then settling time is 3 tau, that is 3 over zeta omega n. So, here my time constant is basically 1 over zeta omega n. So, we know that what is the time constant? This is a time where our system requires 63% of the response. It means this is a time interval where my output reaches 60%. You can say if I plot the line of 0.63. So, whenever my input, you can say sorry, output expression crosses this 0.63, then we can say this is 63% of the output, and this time interval would be time constant t. And if I calculate this value is t equal to 1 over zeta omega n. Okay. So, basically settling time is inversely proportional to the damping ratio. So, if I increase zeta, Ts will decrease, and if you decrease zeta, then Ts will increase. Okay. So, this is the conclusion that zeta increases, Ts decreases. Okay. So, now we would like to see the basic application of this damp system. Okay. So, over damp system, you can say one application is push button water tap, right. So, you had seen whenever you are going to the airport or any mall, you have to see the automatic water system. When you press the button on the tap, it will give you water. When you release it, after some time automatically it will shut off. Okay. So, this will belongs to the over damp. It means initially you disturb the state and slowly it will reach to the off state. So, this will be the category of over damp system. Second example is automatic door closer. You have to provide a certain input, your door will open, okay, and after certain time slowly it will shut. Okay. It means it will take a little bit time to off. So, this is a slow system, right, and this will come under category of over damp system. In the same way, if you like to observe critically damped system, so one is the elevator mechanism, where when you press the button on the elevator 2, your elevator level immediately change from 1 to 2 after a very short interval of time. It means it will take certain time to reach the second level. This time interval you can say would be like this, and this time interval would be faster as compared to over damp. Okay. So, the elevator system mechanism will belongs to the critically damped system. The same way gun mechanism, okay, you can say when you fired a shot, then my gun position will return to the neutral state. Okay. So, this has to be done in a very small interval of time. It means we are considering here speed of the system. So, whenever we have to design a faster system, we have to make a goal to make it a critically damped system. Okay. In the same way under damped system, you can say all string instrument, bells and under damp, where you may get a certain oscillation. You can say a vibrating sound, humming sound is coming. So, that will gives you a under damp system which is having a certain oscillation, or you can say analog electrical circuitry or mechanical system instrument, they will come under category of under damp system, because you will get a certain oscillation because of resonance in electrical network. And in mechanical system, if you are dealing with the you can say spring type of system, then you may feel certain oscillations. Okay. Then we will talk about the steady state error, right. So, what is steady state error? This is the basically the difference between the output response that I want to observe, or you can say my desired response, and the actual response coming from the system. Okay. Suppose if I am discussing my step input like this is my input, and what is happening, my actual output is coming like this. So, the difference between my actual output and this is my desired output, this would be the steady state error. We had seen this thing in the previous lecture session, where we were discussing about the impulse response of the first order system. Okay. So, you can say what is steady state error? We had seen it is the difference between the actual output and the desired output as time t approaches to the infinity. So, here we need to do this analysis at steady state. Whenever we reach to the output state to the percentage of 95%. Okay. So, in that case we have to see whether we reduces the difference between actual and desired output or not. Okay. So, that is why for that analysis we have to use the final value theorem. So, from final value theorem that error would be given like this, ESS equal to limit t tend to 0 E t, right, and where E t error is what? It is the difference of my input, basically it is known as the desired output that I want to obtain at the output of the system, and Y t is my actual output. So, the difference between desired and actual output is the error E t. So, you can see this from this block, we had seen this type of block in unit 1. So, this error is what? You can see this feedback Y s is coming, R s, this is my input and this is the output coming from the feedback. This E s is basically what? E s is, you can say, my input minus output, right, where my input is, you can say in some definition, this is my desired output, where this output is your, you can say this is the actual output. So, this is the error generating at the output of summing point. Okay. And in 90% application we apply here the negative feedback. Okay. So, if we calculate E s, you can say E t in terms of this expression. So, E s s can be, you can say, steady state error equal to limit t tend to infinity E t, where if I take the Laplace transform, this will become limit s tend to 0 s times of E s. Okay. This will come. So, what is E s? From the derivation I have to write the expression for it. Okay. So, if I look what is Y of s, so Y of s is basically g times of E of s. Okay. This equal sign is here. Okay. And then further if I see what is E of s, so E of s is basically R of s minus, here output is Y s multiplied by 1 because unity feedback is here. So, I can write minus Y of s. So, here you can say this is the expression for error. Okay. So, here R is here, what would be my Y? So, from here I can write here Y would be like this, you can say if I solve this transfer function Y of s, this will gives me g over 1 plus g s h s. So, h s is 1, this is g over 1 plus g. Okay. So, here right now it is multiplied by, you can say this is the error term, okay, g term. So, here it will be multiplied by r, this will happen, and further if you simplify it, this will become r over 1 plus g. Okay. So, if you solve it further, you will get E of s s is equal to this expression limit s tend to 0 s E s is equal to limit s tend to 0 s dot r s 1 plus g s. Okay. This simple calculation you can try yourself, where R s is basically the input in S domain, and here this E s s will gives you the steady state error. You can see this is the E s, this is the error in S domain. Okay. So, here we can vary the value of R s. One, we will assume R s is impulse, R s is step, parabolic and ramp, and then we would like to see what would be the steady state error. Okay. So, for unit step input I am assuming R s is 1 over s, this is my error expression that I derived. Okay. So, here I will put 1 over s in place of R s, s will cancel out, this will become, and I can say this term can be written as 1 over 1 plus limit s tends to 0 g s. So, this term is basically K p, which is the position error constant. If I am having the feedback h of s, then K p can be equal to limit s tends to 0 g s h s whenever we are having a finite value of feedback system. If h s is equal to 1, you will get this expression of K p. If h s is finite, we will get this expression of K p. So, K p is here position error constant. Okay. And if we see this response, we are applying the step signal, and this is my output, and this is the difference is coming between my actual and desired output. So, this is my input signal equivalent to the desired output, and this is my actual response coming from the system, this type of oscillation. So, this is my actual output, you can say Y t. So, in this case ESS equal to R over 1 plus K P, or if you assume any input here, you can say if R T, you can say if reference input is this much, R times of this, if it is having certain amplitude, then it will come here. If it is unity, then you will get, you can say if amplitude is unity, ESS equal to 1 plus K P, otherwise you will get here certain amplitude R. For avoiding the confusion, you can assume A will come as a amplitude in the numerator. Okay. So, this is the steady state error for step input. Now, I will change my input to the ramp. The ramp is basically known as the velocity input. R s equal to 1 over s square, same expression. So, here you will get what, s multiplied by 1 plus G s will be happen. I am assuming H s is equal to 1. If you want, you can use H s here also, and we are making R s equal to 1 by s square. So, it will multiplied by 1 over s square. So, s will cancel out, 1 over s will come in denominator. This is s plus s times of G s H s, if I assume H s present in the system. In this case, I am assuming H s equal to 1, that is why I am getting this type of expression. Now, I have to apply limit s tends to 0. If I apply this limit here, this term would be 0, okay, and this term will be here limit s tend to 0. If I combine it, this will make another term which is k v. This is the velocity error constant. Okay. So, here whenever my H s is equal to 1, this is the expression of k v. Okay. Otherwise, I can say my k v is limit s tend to 0 s dot G s H s. Okay. If my H s is unity, in that case I will get limit s tend to 0 s G s. So, this is the k v, velocity error constant. So, if I apply the ramp input to my system, so this is my reference input, or you can say my desired output, right, and this is the response coming, actual output coming like this. There is a finite difference in between them, where my steady state error is given by this. If this amplitude is unity, so ESS equal to 1 over k v. If we are having a finite amplitude, then it would be given by A over k v. So, R is basically the amplitude present here. If my input is R t, then it is giving like this. Okay. In the same way, when we look for parabolic type of input, so we are saying it is a acceleration type of input. It means my R s is 1 over s cube. If we evaluate in the error function, s square will come in denominator. Okay. Then I will apply limit s tend to 0. This term will go to 0, and this term you can say will be your new term, acceleration error constant. So, whenever my feedback is finite, so my k a expression would be given as limit s tends to 0 s square G s H s. If my H s is equal to 1, so we can say this would be the expression of acceleration error constant k a. Okay. So, these are the various acceleration error constant, position and velocity error constant, and this is the graph coming. You can say this is my parabolic input, and my output is running around this input. The difference between them is given by k of a, steady state error. Okay. So, in the next lecture, we will discuss about the dynamic error coefficient, and we would like to see the basic numerical over it. Okay. So, thank you for today.